Hey there. Today we're going to talk about sampling. And before we begin talking about sampling and techniques and things like that, we need to define a couple of very important terms. The first term we're going to talk about is the population. When we're talking about sampling, population means it's defined as this big group that we're trying to find something out about. So this could be everybody in the world. That's a sort of a literal definition of population. But it could also be something like, well, it could be all the registered Democrats in the U.S., or all U.S. college students, or all of the customers of a certain company. But population does not need to be a population of people. It could also be all of the products produced by a certain company, or it could be all registered vehicles in a state. In other words, it's something that it's a large group that we want to know something about, but it's too big to go out and test every member of the population, or to ask every member of the population a question, or to go observe every member of the population, be it a person or a thing. They're just too numerous. And so sampling is a way to find something out about the population. We use a sample, which is a small group, smaller group, taken from the population, and we're going to test, ask, observe. We're going to do something with the members of the sample, and because it's a smaller representative group from the population, and that's going to tell us something about the population. It's going to give us an estimate about that should sort of hold true for the entire population. Now, I mentioned a term in there, representative. Finding a good sample is a real challenge, and one of the hardest things to do in research. And what that means is you want a sample that is exactly representative of the members of the population, but it's very hard to do. So for instance, if you want to survey all registered Democrats in the US, how do you get a group that is exactly representative of all Democrats? You can't just go to your political science class and say, hey, who here is a Democrat? Well, I need to ask you some questions. And then use that as representative of all U.S. Democrats, because these are, college or graduate students, and, they might not have the exact same views as the entire population of Democrats in the United States. You can't even just ask, generally speaking, randomization is better. In other words, what you want to do is you want to get you want to just sort of grab members of the population out at random. And that will be a nice, that ought to, because of randomization, they ought to represent the same distribution of people who feel sort of middle, and I keep using the term people, but this could be items or whatever. It could be sort of the ones that are middle of the road, the ones that are at the extremes. But it's hard to even get randomization. So for instance, again, go back to the same example. If you want to survey Democrats, you can't just call up a bunch of registered Democrats, because it matters when you're calling them. I mean, okay, you can, but it won't necessarily be a 100% representative sample, because, you might, if you call them during the day, you're only going to get the people who are home during the day, and that might not be the same as all Democrats. So many, many, many challenges. But essentially what you're trying to do is you're trying to get representative, and usually the way to do that is, to the extent that you can, try to get randomization in terms of your selection from the population. But basics are here. Population is the whole. A sample is a smaller group that it's more manageable, and so you're trying to get some truth out of the larger group. Oftentimes what you're trying to figure out about the population is the mean, the average, or the average and maybe the standard deviation. This could also be a proportion. So again, if you're surveying people's political opinions, you might be interested in what percentage supports some sort of gun control legislation. And so that's what you're really trying to figure out, is like, okay, well, I think that about 60%, we think that maybe it's 60%, so we're going to take a sample and see if that holds true based on our sample. So it could be a proportion, it could be an average, maybe you want to know your standard deviation and variance, things like that. One thing that is always true is that the larger your sample, the more likely it is to be accurate in terms of making predictions about your population. So if you are interested in finding out about people's political viewpoints, and you ask 2 people, you might get 2 extremists. But if you ask 1,000 people, they're much more likely to represent the entire population that you're interested in. You'll certainly get some extremists, but you'll get extremists on both sides. And you'll get a lot of middle-of-the-road people. And so it'll all sort of balance out, and you're much more likely to sort of end up at an average that is more representative of the average of the population. So big samples, to the extent that they're possible, tend to be good in terms of their predictive power with regards to the population. All right, so now I want to talk about, I'll use a whole new color. We're going through the spectrum today. Talk about another concept that is extremely, extremely important. I alluded to this in a previous video, but I really want to talk about it at length here and sort of hammer it home. It's called the Central Limit Theorem. And what the Central Limit Theorem says is this. This is very important. It's actually one of the more challenging concepts in statistics as it regards to sampling. I think a lot of people sort of goes over their heads, but we're going to talk about it a lot. We're going to give some examples. Central Limit Theorem says this. You take a sample from a population. The probability distribution for the mean of your sample is going to be normal around the mean of your population. Let's draw this out. I know that seems like a lot of words, but it actually kind of makes sense. This is a probability distribution. So on the y-axis, we have the probability of getting any specific value. Turn my hand to it like this. First time I've done that in one of these videos. Gone vertical. All right, so that's probability here. These, along here, we have values that the sample mean might be. Remember, we've taken a sample. We're measuring that sample mean, the average of the sample. They could take any of these values, and they center around the population mean. That center line here, that vertical line right here, is the population mean. And all along here are values that the sample mean might be. So we're taking a sample, could be anywhere in here, and all of this represents the probabilities, right? Where the curve is higher, it's a higher probability, and where the curve is lower, it's a lower probability. It obviously all adds up to 100%. So what does this tell us? It means that we're likely to end up with a sample mean, a lot more likely to end up with a sample mean that's close to the population mean, as opposed to being extremely far to the right or to the left. These are much less likely. Being close to the population mean is likely. Also notice, I mean, these are all the properties of a normal distribution, that it's symmetrical. So we're as likely to be higher to the population mean as we are likely to be lower than the population mean. But it's all centered around the population mean, and we have this nice bell-shaped curve in terms of probability. Really important point here. This is true. The tendency, or not the tendency, the fact that that sample means will be normally distributed around the population mean is true no matter what the distribution looks like for the population mean. In other words, the distribution of values in the population mean, it could be a uniform distribution. The probability distribution for the population mean and for the population could look like this. It could be something totally bizarre. But both of these are going to have a mean. And when you take the sample mean is going to be normally, the distribution for those sample means is going to be normally shaped. Now, an easy way to think about this, or I don't know if it's an easy way to think about this, an easier way to think about this is you say, look, if you take a whole bunch of samples, right? You take 1,000 samples. If this were a distribution, instead of being a probability distribution, but this were a distribution like a histogram, right? What you're going to end up with, this is my histogram. Ooh, boy, it's bad. Are values that are normal. So if you took a whole bunch of samples, the means of each of those samples, are going to be normally distributed. let's actually look at it. I'll give you a specific example here. Okay, so let's say we are interested in finding out how much the average U.S. families, or we'll say the average person in the U.S. spends per week on groceries. So we'll call this groceries spend per week. Now, let's say the actual average is $70, right? That's the actual amount that the entire U.S. population spends on groceries per week. I made that number up. If you know the real number, then please don't write to me. That's the actual. That's just the number I wrote, not the actual number. But let me say the average citizens and average person in the U.S. spends $70 per week on groceries. Now, if we took 1,000 samples of 100 people each, what we would get, so I said 1,000 samples in each, with a sample size of 100 in each of those samples, what we would see is the means of those samples. These are the sample means along the horizontal axis, would be normally distributed. The distribution of those sample means would be normally distributed around $70. In other words, most of those samples of 100 people each would have an average that's pretty close to 70. And there'd be a few outliers, higher than 70, and there'd be a few outliers that were significantly lower than 70, but mostly they'd be around 70. Now, what if we took, so this is 1,000 samples, 100 each. 100 people in each sample. What if we did one where we did 1,000 samples of 500 people each? Well, remember that larger samples are generally better, more accurate predictors of the actual value in the population. So we're still going to see a normal distribution centered around 70. It's going to be harder for me to draw because I've put my center line all in early. Makes it much harder for me. But let's try this. What you're going to see is a distribution that goes more like this. That was remarkably good drawing. You got to give me credit for that. I mean, maybe you're better, but for me, that was as good as it gets. So what we see here is it's still a normal distribution. This is still a normal distribution right here. But it's taller, meaning that more of the values are centered around $70. There's fewer outliers, and they're not going to be as far away. So those samples of 500 each, there's going to be fewer that are farther away from 70, and more that are sort of clustered right around 70. Because larger sample sizes are better predictors. Now, let's say we took 1,000 samples of 20 people each. Still a normal distribution, centered at 70, which is the actual value of the population, but we're going to see something more like this. What we're seeing here, still normal, but a lot more outliers, because 20 is not really, with a sample of 20, we might get pretty far away from 70, the actual average of the population. So we might see, groups that are pretty far away from samples that are pretty far, that have a mean that's pretty far away from 70 in either direction. There's still going to be mostly, there's still going to be more that are clustered around 70, but there's a much wider distribution. All right, so let's talk about why is this important? Why is the central limit theorem important? I want to find the. It's important because we know that this distribution is going to be normal. The distribution of our sample means is going to be normal around the actual population mean. It allows us, and we know things about the normal curve. I mean, it's what we've been looking at in the last few videos. We can figure things out based on standard deviations, a number of standard deviations away, confidence intervals, and we can say, once we have a sample mean, we can say, well, okay, now we sort of have an idea of what the population mean is, and because we know things, we have confidence intervals based on the normal distribution, we can say, okay, well, we can be confident that the actual population mean is going to be within this range. And we're going to do a lot of examples of this. I just want to put that out there right now. Because we know things about the normal curve, and we have these z-tables and things like that, we can actually make accurate predictions and know kind of how accurate they are about the population mean based on the size of our sample, and obviously the standard deviation and the average that we measured in that sample. So this central limit theorem, because it says distribution of sample means are going to be normal around the population mean, gives us tons of things that we can use later on. So let's take a look at an example to illustrate how we might actually use sampling in sort of a real life situation. Let's say we're a marketing firm, and 5 years ago we did a study on Americans' internet usage, right? And in that study 5 years ago, what we found was that, let's say we did a very extensive study 5 years ago, and we found that average internet usage from that study 5 years ago was 3 hours per day, and the standard deviation was 1 hour per day. And we've decided that possibly internet habits have changed in the last 5 years, and so we've decided to update our study. And so what we did, we took a sample of 2,000 Americans. We'll call that a sample. That's our sample size, is 2,000. And so we could say n equals 2,000. Sample size is usually denoted as n, so say 2,000 Americans. And in our new study, we got a good group. They're very representative. It's a good mix of representativeness in terms of ages and genders and professions and incomes and educational background. It's an excellent sample. And what we find is that our sample mean is 6 hours per day. What does that tell us? Well, because the central limit theorem says the sample mean should be normally distributed around the population mean. Let's say, so this was our assumption, right? Our assumption was, the thing that we're interested in knowing is the average of the population still 3 hours per day, right? And if that was the case, if the population average still was 3 hours a day, what's the likelihood we'd end up out here at 6 hours a day? Remember, the standard deviation is 1 hour per day. What's the chance that we'd end up 3 standard deviations above the mean? And by the way, there's extra math involved with taking the distribution, the standard distribution of a sample mean. So we're not even really, it's actually more than 3 standard deviations, but just based on this, I mean, we took a sample of 2,000 and we got a mean that was 6? What kind of conclusions can we draw? Well, I think it should be pretty obvious that we can say, you know what? Pretty unlikely that the average is still 3 hours a day. That does not seem like it would be very possible, considering that we did a 2,000 person sample. That's a pretty decent sized sample, and we got 6 hours per day as the average of that sample. Unless our sample was crazily unrepresentative, and I told you it was a good sample, there's just no way. There's no possible way that we could get 6 hours if 3 hours was still the average. So what do we assume? We assume that the average number of hours that Americans spend on the internet has changed in the last 5 years. There's a lot of evidence to suggest it has gone up and gone up significantly. So this is actually one extremely common usage, and we're going to be talking a lot about this more later, of sampling, and it's called hypothesis testing. And basically you say, I have this hypothesis that I want to check out. We haven't even done the math around this, but this is just sort of an obvious case. We have this hypothesis. The hypothesis here is Americans spend 3 hours per day on the internet because that's the last measured value. So this is our hypothesis. That's called the null hypothesis, and we want to say, we also have an alternative hypothesis, and the alternative hypothesis is no, that's actually changed. that value is no longer 3 hours a day. And what we're looking for is evidence to say we can reject the null hypothesis, we do think there's been a change, or we don't have enough evidence, and we're going to keep on believing that there's 3 hours per day as the average for Americans. And this sample here gives us plenty of evidence that actually we're going to reject the null hypothesis. We're going to reject our original hypothesis, which is that Americans spend 3 hours, and say, nah, it's probably something a lot more. And so that's how you might use sampling kind of in a real world type situation.